Okay, so we'll talk kernel density estimation. Okay, and this is, when you run R, this is like this useful, very useful thing that gives you an idea of kind of the shape of the distribution, okay? And, we kind of did stuff like this when we did our bootstrap, right? In our bootstrap, we kind of got all of these things at the end. And so let me just demonstrate what kernel density estimation looks like in R. So here I'm going to just take, generate a sample. I'm going to do R norm. I'm going to just take 100 points from the random normal distribution, right? So when you do R norm, this has a mean of 0 and a standard deviation of 1. And pretend like my feelings aren't hurt. And anyway, so we got a mean here, we got a standard deviation, and we want to know, like, okay, what does the shape of this thing look like? And so a lot of times we do, we'll create a histogram, right? And so here I'm just doing all of this in base graphics, and that's fine. And and this is a histogram, and at the core level, a histogram is kind of one of the simplest versions of kernel density estimation. It's just the kernel is very blocky. And in effect, we often use a histogram as a proxy for what the distribution looks like, right? So we say, okay, well, we look at this and we say, well, does this kind of look normal? And we go, yeah, it looks pretty unimodal and pretty symmetric, so we'll say that it's normal, right? And we've learned, as far as creating histograms go, oops, what is, if it's not bins, what's it called? Bin width? Breaks. Breaks is what it is, right? Okay. Oh, what? It is really angry with me. Is breaks not the thing? Okay, and we can alter the number of breaks that appear, and here is a histogram where the bin width has been made smaller. Okay, and this might give us a better idea of what our sample looks like. Okay, as far as the density, and our sample, we just have 100 points. But based on this, we might want to try to create an idea of what the density looks like, right? We want like a kind of this smooth picture. We're used to seeing normal distributions look like this, and so we might say, we might just do density of the samp, okay? And this is going to just print out a bunch of, I don't know, summary information here, okay? But you throw in plot, you throw density of the samp into plot, and boom, now you have this nice smoothish looking, smoothed out thing, all right? And this is kernel density estimation. We are taking a finite sample, we're taking just a sample, observed sample that we have, and we throw it into this thing, and what it spits out is kind of an estimate of the density, and really, there's a whole bunch of math that goes into it, and here I'm going to just cover from a very high level conceptual perspective, and we'll kind of play around with it and get an idea. And again, I'm not going to put this on the final exam, so don't worry. We're just going to cover this from a high-level perspective, and we get this shape, right? And as far as density estimations go and talking about what the distribution looks like, I think it's most useful as a graph, as something we can visualize to see what the distribution looks like, okay? it's true we can kind of come up with some. I suppose we could describe the shape of this thing not with a picture, but with a bunch of math shape, like a function that describes this, and I think that's less useful. Okay, but here we get this, we get a picture here, right? And creating this picture that looks nice and smooth and things like this has only become possible with computers that do all of these calculations for us very quickly, because there is a decent amount of calculations going into this, and anyway, so the computer, so I consider this still a computational statistics thing, although really for us it's used as a tool to visualize what the thing looks like, right? And then so you look at this and you say, does this look like it could have come from a normal population? And we'd say, yeah, I think so, right? Okay, and certainly it did, right? Because we generated our sample from the normal distribution. Okay, so what is kernel density estimation? All right, so imagine we've taken a sample, and so this is our number line, and we will say, let me mark off our number line. We'll say here's 0, and here's 1, and here's -1, and whatnot, right? And so as we we draw data points from our norm, and I'm going to just say here, here's a sample of 3 data points here, okay? And I'm going to just kind of mark this on the number line. Now, if I were to create a histogram here, my histogram would take this thing, and we would just put bars where these data points are. And so our histogram after 3 data points would look, however tall our bars would be, our histogram would look something like this. And it's just, with the accumulation of many more data points, okay, and perhaps they won't all be centered at the thing, as we accumulate more and more data points, we would get something, so this would be the histogram, and then as we get more values, basically, we're going to get kind of more in the middle, and then fewer out here. But we're, a lot here, and then it drops off, and then therefore, after we do this, the bar representing all of these data points will be quite high, and then we'll get something that looks kind of like this as far as our histogram goes. Something like that, right? Okay. So this is our histogram. And if you think about the way a histogram works, is that basically for every dot that appears here, okay, basically each dot or each value basically increments the histogram by, like a little chunk, right? Like it's like you're stacking Lego bricks, okay? And for every dot, it grows, and so after 10 dots in this zone, this bar in the middle will be 10 units high, okay? And then if there's six dots over here, the bar over here will be whatever, 6 units high or something like that, okay? So you can think of kind of the histogram as a way that we're just adding up bricks, okay? And we define kind of this range of where we say this dot belongs to, this bin, and this dot belongs to this bin, and things like that, okay? And that's kind of the way we can think about a histogram, right? So we say, each dot in a certain, quote, bin, becomes basically a brick that we that we add. Okay, we add to the height of each bar. Okay, and that generates our histogram. We can think of kernel density estimation as something similar. Let me just get this. As something similar, except instead of adding bricks, these rigid bricks, we use what we call a kernel. Okay, and so what the kernel looks like is that centered at each data point, okay, we're going to add, so instead of adding bricks here, okay, we will add kernels. Okay, and there's a whole discussion of how these kernels work, but basically you can imagine and there's a variety of kernels, but for the beginning I'll use the Gaussian kernel. And you can imagine this little normal distribution centered at each of these data points. Okay. Okay, and then we would add these up, and so if these were my kernels here, then our density estimation would look, it would look rather lumpy. It would look something like this. Okay, because these parts in the middle have added to each other to kind of do this, right? And that's effectively what we're doing. And we could change the kernel, and we can change the properties of the kernel, or the width of the kernel, and all of this stuff, so that if we wanted to, instead of having our kernels look like this, if we had the kernels be really wide, okay, and all of this gets accentuated just because I only have 3 data points here, okay, like I could say the kernel over here is really wide, and the kernel over here, this is a terrible looking picture, you know, something. We're going to add all of these together, and then what this becomes, when you add each of these these graphs on top of each other, then you end up getting, in this case, with just 3 data points, you'd get something, you know, much more smooth. I don't know, the overall thing would look kind of like this, okay? And it's just this, I'm hoping we can picture what's going on when we add this graph on top of this graph, and we're kind of getting something like this, okay? And that's effectively what we're doing, okay? And you know, as far as kernels go, we have a variety of them, and let me just take us to Wikipedia to okay, so we have all, you know, these kernels, and so we have uniform kernels, kind of like this rectangular shape, this triangular kernel. This is more like a upside down parabola. Okay, we can use this. This is kind of this, you know, so here's the Gaussian kernel, but we have these quartic and triweight and tricube and cosine kernels, just different ways to take. We're going to just basically take one of these little graphs, centered it at each data point, and just add them to each other, and this this creates kind of like this smoothed out function of what our thing looks like, okay? And here's kind of a picture of exactly that going on here. So here we have 1, 2, 3, 4, 5, 6 data points, and so with the histogram, you know, wherever this data point lies, the histogram grows. We're just stacking bricks. So here we have, you know, 1 block at this point, 1 block at this point, no blocks here. We have 1 block here and 2, and so that bar ends up being twice as high. Using the same 6 data points here, I've got 3 kind of these Gaussian curves added up right here, here, and here, and they sum up and they kind of form this nice little peak here, and these ones form this, and we get this shape here, right? And you know, and I think it's a valid question to ask which shape is more accurate or whatnot. And well, in effect, they actually kind of capture a very similar picture in both cases. You know, we kind of have this a little bit of a gap here, and that appears right here, and it also appears here. But here it's a lot more rigid and straight, and here it's, you know, smoothed out more. And we can see you know, what is this going to look like depending on how the thing goes, right? So depending how wide you choose your kernel to be, your resulting thing could be a lot more jagged or a lot more smoothed out, okay? And there's a lot of discussion as far as, you know, what is the right size kernel you should use, and you know, maybe it's a little bit, it's kind of just like everything else in life. It's a nuanced discussion, and there's no one answer that says this is the best in all cases, okay? But you know, let's just kind of play around with this, and let's just show you what happens here, okay? So let's say I take 2 data points, okay? So this is, we'll call this sample 1, and I'm just going to say, let's say I took a random, not a random sample, but I took a sample -1 and 1, okay? And let's see what. Here, let me rearrange my tiles here. Let's do. Let's put the console here and the plots over here. Okay. Okay, so here, you know, I just put in -1 and 1, and you can kind of see, you can picture what's going on, right? We just have 1 Gaussian curve here, and then we have another Gaussian curve going on over here, and where there's some overlap, even though there's no actual data points here, they form this thing, okay? Now, let me pull up the things for the density function. We can alter the width. We can alter the actual type of kernel that gets used. And so let me just kind of show you what happens when we change some of these things. Okay, so I'm gonna, instead of using the default thing, let me just change the kernel to I think it's called rectangular. Okay, and you can kind of picture what's going on here, and you get this funny looking thing based on the width. What's going on there is, here I've got at -1, and over here I've got 1, and there just happens to be kind of maybe I should use a different color here. Okay, so we'll say, you know, here's a rectangle, and it's not a perfectly rigid rectangle, but let me just kind of slightly. Okay, so I got a rectangle centered there, and then we got another rectangle right here, and let me just kind of stagger it off. And so when we add these two together, you end up getting kind of the picture that we saw below. When they add together, in this middle part, because there's two, it forms this shape here. All right, and this is the resulting picture that we have when we mess around with the kernel density estimation here. So we get something that looks kind of like that when we have things centered at -1 and 1. Okay. Similar things, we can look at the triangular. Okay, and so you have a triangle centered at -1, a triangle centered at 1, and basically when you add a triangle going down and a triangle going down in the other way, they kind of flatten out right here. Right? I forget what are my other options here. Epon, however you pronounce this. Okay, so we have that. It's like that's fun. All right, and all of these look kind of ridiculous when you're doing kernel density estimation with 2 points, which on a practical level you would never actually do. But just for the illustration of how a kernel density estimation works, I think we can understand in our minds what's going on here, right? So whoops. Okay, so we'll do cosine, okay, and that looks a lot more smooth as well. Okay, let me try changing the width.
What's the default value?
The default is the Gaussian. The default one uses the Gaussian kernel here. Okay. Oh, I'm sorry, the bandwidth. Okay, so the smoothing, bandwidth, the kernels are scaled. The bandwidth used. How do we? I don't even know what. Okay. So let me just change my bandwidth. So I think. So with a bandwidth of 1, this is what our thing looks like. So it's much more smoothed out. Okay, and you can, if I do bandwidth 10, you can see what's going on. It stretches all the way now out to negative 30 and 30, which it probably should not be doing, right? So this is effectively saying we're using a Gaussian distribution with a standard deviation of 10, right? And so with a standard deviation, if here, when you're changing the bandwidth, you're putting a lot of assumptions about what our data looks like. And so basically, when we're putting in the bandwidth of 10 and our two data points came from -1 and 1, that gives us a lot of information about where the center of our distribution is, or center of our density would be, but all of the information about the width is coming from this bandwidth specification, and that's really telling us about the standard deviations here, okay? Whereas, I can shrink this down, okay, and we get something similar to our original thing, and as I shrink this down further, we can see clearly the shape of our density change as our bandwidth goes, okay? And so the default value used for the bandwidth is calculated for us with the density function in R, and I forget the exact method that is used to calculate the bandwidth, but a lot of research has already gone into it. This whole section in Wikipedia's page talks about bandwidth selection and just some kind of these rule of thumb methods for selecting an appropriate bandwidth here. Okay, let me just kind of show you what bandwidth looks like with if we use other kernels. So here you can see just two rectangles being added, and as far as triangles go, it looks exactly as we might expect. Cosine looks like parts of kind of the cosine curve, and I forgot what that epon. Okay, and you kind of get these things, and as we can shift around kind of the kernels and see how the bandwidths work here. Okay, and so anyway, as we increase the sample size, okay, so if I now take a sample, we'll call this sample 3 or sample 2, and this I can use -1, 0, and 1. We can see how the plot of our densities change. Okay, so here I've got -1, 0, and 1, and this is with the default Gaussian kernel, right? And then we can increase our bandwidth or decrease our bandwidth to kind of smooth things out, or make it a little bit more jagged. Okay. Same thing with rectangular. As I increase or decrease the bandwidth, let me just get rid of the bandwidth parameter there. You know, we get these funny looking things going on here, and that's strange actually. Why am I getting I'm not sure why I'm getting a dip at the 0. Okay, that makes more sense. All right, so anyway, this is just basically how kernel density estimation works. I've just given you a conceptual idea without getting into any of the math, and I hope that's okay as far as how this goes. But it is an incredibly useful tool, because as you perform random sampling or whatever it might be, okay. Let me just kind of load up. Nope. Session to set working directory. Let me just choose our a data set from our. We'll take the. I think this is where my Latino education data set. Nope, that's not there. Okay, sorry. Let me just find where that data file is for the Latino education attainment. Shoot. Where did it go? Okay, comparing groups, data. Okay, so we'll use this. Here it is. Latino ed.csv. Oh, that's what it's called. Okay. Sorry. Okay, there we are. And so here we can take a look at this, and we can create a density for achievement, right? So we can do plot density achievement. Oops. Okay, and we get this curvature, right? And so we can see, you know, what would happen if I messed around with the bandwidth, if I changed it to, in this case, the bandwidth is a lot more jagged. Here, it gives you an idea. It tells you the bandwidth that it calculated that it should be using is around 4.2. but we can see what would happen if I change that to something, you know, smoother, okay? And from looking at this, we get an idea, you know, is this something that could be normal or not? And the answer is, well, maybe. It looks a little bit left skewed, okay? We could subset this by taking a look at, you know, whether they're from Mexico or not. And we can compare each of these things, right? And so actually, let me do, we'll do this, and then instead of plot, I'm going to do, I think I can do lines. Color equals, we'll do red. Oh no, that's not color. Oh shoot, of course. And so we can plot these on top of each other, and you know, now we're running into problems here because I probably should define this. So anyway, this is one of the problems of base graphics, is that the plots don't adjust as you change these things. Okay, but you know, you can kind of plot these two things against each other, the densities, and the truth is that the underlying data isn't this smooth, right? If we actually created a histogram rather than the density, so you know, I think the picture would become more clear to us. You know, here's a histogram of education achievement levels for people coming from Mexico. It looks a little bit more like this. We can change the number of breaks to get it, you know, a little bit more rigid, and we can compare kind of the shape of this thing versus our kernel density estimates, and it does reflect what this looks like, but it also has really drastically smoothed things out, right? So, you know, here's what it looks like. This is different histogram bin widths, and we end up getting this, okay? And so anyway, kernel density estimation, it is useful, and you can talk about changing the kernels that we've used and just see the shapes that happen. Okay, so this is rectangular. It ends up getting you get all these wiggly bits, but the overall shape is there as well. Triangular looks a little bit nicer, okay, but also still a little bit jagged. And then everything else tries to, because you're adding these curves that are, you know, smoothly differentiable. When you add them together, you get things that are also fairly nice to bring together. Okay, and because the ends of each of these kernels, if we look at these, right? So here, you know, they get jagged because the edges are very harsh. Even the epon, I don't even know how you pronounce that. You know, the edge here is very jagged. Over here, as we look at these other ones, the edges kind of smooth off, and that's why they add up a little bit more nicely. Okay. But anyway, so this is that's kernel density estimation. All it is we're just taking these kernels, these little shapes, we're centering them at each data point, and then we're just summing them up to get this overall shape, to get an idea of what the distribution might look like. Okay, without and at the base level, what's going on is the same thing that's going on as a histogram. In a histogram, though, it's a very strict rule of you count how many points are in a certain thing, and you build up the bar that high. For each of these things, you're effectively you're taking each of these curves and you're basically counting how many are within kind of this vicinity of a curve and vicinity of a point, and then you're adding all of those curves up together. And so it gets the math and the computation there is a lot more intense. Thankfully for us, R has implemented this very nicely with their density function. It's also implemented in ggplot, but I don't remember all the commands off the top of my head. And we can do kernel density estimation this way. Okay. Don't worry about seeing this on the final or anything like that, but I just thought we would talk about this. On Friday, I'll go over kind of some of the answers from homework 6 that I just posted. I do recommend that you check it out and try it out. I think when you work through some of it yourself, you'll learn from it. Okay. All right, we'll see you guys on Friday.